In the last video, we looked at dissolving compounds in water to make aqueous solutions. The big picture we saw there is that whatever particles were present in the original substance ended up swimming in the water surrounded by water molecules in the solution. When I had an ionic compound made of ions, I get ions in solution. When I have a covalent compound made of molecules, I get molecules in solution. Now I'm going to look in a bit more depth about what happens when things dissolve in water, and I'm going to jump ahead in your textbook to section 11.2. Yes, we're still in chapter 4, but there's some interesting, useful information in chapter 11 I'm going to steal and add here. We're going to look at electrolytes, which are substances that dissolve in water to make a solution that conducts electricity. Electrolytes dissolve in water to make a solution, and I'll abbreviate that SOLN, that conducts electricity. So what is necessary to have a solution that conducts electricity? What is necessary to have anything conduct electricity? We need two things. We need to have charged particles, and they need to be able to move. I'm going to point out the charged particles and how they're able to move as I go through the subtypes of electrolytes, the strong electrolytes, the weak electrolytes, and the non-electrolytes. So first I'm going to start with the strong electrolytes, ones that are completely or 100% dissociated in water. What dissociated means is that it's broken into charged particles. To be an electrolyte I need charged particles, so strong electrolytes are ones that completely break into charged particles in water. The other thing that's necessary to be an electrolyte is that the charged particles have to move. Ionic compounds don't conduct electricity on their own because the ions are locked in the solid. But once the ions are dissolved and swimming around in water, then they can move. So, how are we going to recognize that a compound is a strong electrolyte when we see its formula? You're going to look for soluble ionic compounds. That's most of them. And a key exception to that is strong acids are also strong electrolytes. More about them in a minute. Let's start with the soluble ionic compound. I have a favorite ionic compound. I don't know if you do. Mine is table salt, sodium chloride. And we looked at what happens when you dissolve sodium chloride in water in the previous video. First question I have to ask myself is it ionic or is it covalent? I see metal and non-metal. That tells me it's an ionic compound. Oh, it contains ions. So when I dissolve it in water, and you can do this before I get there, I hope, pause the video. The ions that were already present end up surrounded by water molecules, or aqueous. Remember we talked about this example before. I don't see the water, H2O, explicitly in the equation because we only want to show things that change in chemical equations. The water is not chemically changed, so I don't show it explicitly. It's implied when I say that the state is aqueous. So I've made charged particles in a liquid solution. I have charged particles that can move. This is an electrolyte. Every little bit of salt that dissolves makes ions. It's a strong electrolyte. It's 100% dissociated. It's 100% broken into ions. Now, what's the picture on the right-hand side trying to tell me? It's showing me how I can experimentally confirm that a compound is an electrolyte. I've got an electric circuit with a light bulb in it, but there is a gap in the circuit. I've got these metal electrodes here, and if there were no solution in the beaker, There would be no way for charges in the wire, the electrons in the wire, to complete the circuit and have the light bulb light up. But in the solution, it's not electrons in the wire that carry the solution. When I dissolve potassium chloride, an ionic compound very much like sodium chloride, just a different alkali metal ion, I got positive ions and negative ions. And because I have charged particles, this is an electrolyte. Positive ions move towards the negative, negative ions move towards the positive, charges moving in every part of the circuit, and the light bulb lights up. Now, I'm sorry I'm not there with you. Normally I would show you this, but there is a key here for me to remind you that there is an animation that I will link on your Moodle page for you to see in a cartoon kind of way what happens when we dissolve sodium chloride in water. All right, let's do some more examples. Next compound there is sodium hydroxide. Now, just as an aside, I think that's your favorite strong base. All soluble metal hydroxides will act as bases in solution. Some textbooks will tell you, up where I told you about how to recognize strong electrolytes, they'll include strong bases as strong electrolytes. But you know, I don't have to include that there. I don't need more to remember. This already fits the category of an ionic compound. I see metals and nonmetals. So I don't have to know it's a strong base to know what happens when it dissolves. I see an ionic compound. What happens when an ionic compound dissolves? The ions that were already present swim free in the solution. Go ahead and finish the equation. All right, the ions that were already present swim free in solutions. Sodium ions are aqueous and the hydroxide ions are aqueous. Now that hydroxide is a polyatomic ion that contains two nonmetals. There's oxygen and hydrogen in a hydroxide. Don't you dare break covalent bonds when you dissolve something. Covalent bonds are way too strong to break. That would be a chemical change, not a physical change. Dissolving is just a physical change. Now, just one more little thing since I was talking about strong bases. Just a little reminder of what that means. In aqueous solution, that produced hydroxide ions, and hydroxide ions are the species that indicate to me I have a basic solution. All right, what's my last example? HCl gas. Now that may be a surprise to you. You've probably only ever seen HCl aqueous hydrochloric acid with the HCl already dissolved in the solution. And that's because it comes safely and cheaply from the chemical suppliers like that. We would never have you work with the gas. But in its pure state, hydrogen chloride gas is a gas and it is a strong acid. I'll talk to you more about how you know that on the next slide. All right, so I'm going to write you an equation for what happens when HCl gas dissolves in water. And this is not like we saw in the previous video, so maybe you want to wait for me to get this written down. What I know is that it's an acid. And from high school, you know what acids do. Acids supply H+. When I put it in water, which is a liquid, the HCl will donate an H+ to the water. If the HCl loses H+, it becomes Cl-. Watch the charges. Charges are important. Now I made a charged species in polar water, so it's going to get surrounded by water molecules. It's going to end up aqueous. What happened to the H+? The HCl lost it and the water gained it. So it becomes H3O+, and because it's charged, it gets surrounded by polar water molecules. It's aqueous. That's called a hydronium ion, and that's the species I associate with an acidic solution. Some of you are familiar with the equation being written this way. Some of you may have seen it another way. It is quite common for novices to write that HCl makes H plus and Cl minus. That's a widely used shortcut. So, I would never tell you were wrong for doing something that's commonly accepted. Let me tell you why I like the first way better. In acid-base reactions, the proton, the H plus, is transferred from the acid to something else. In the second, simpler equation, it's just looking like the H plus is swimming around by its own in solution. It really doesn't. What happens is that for a water molecule, the H plus sticks on it and makes H3O plus, hydronium. So can you use H plus? Yes, if you know that I know that you know that I know that there's really no H plus in the solution. It's really just an H plus stuck to a water. It's really a hydronium ion. I prefer the former way. Let's see by the end of the semester if I can get you to prefer it too, but you're not wrong if you do it the other way. All right, so HCl, a strong acid, first, is an electrolyte. Yes, it is. We made charged particles. And is it a strong acid? Yes. This reaction went to completion. I drew a single forward arrow. You remember at the beginning of this chapter, I talked about reactions either going essentially to completion with forward arrows or equilibria that appear to stop with reversing arrows. When I say it's a strong acid, that means it goes to completion. It's 100% dissociated. It 100% turns into ions. I'm going to say it goes to completion. All right, so how are you going to recognize a strong acid when you see them? I'm sorry, I'm going to want you to memorize this list. I want you to memorize very little because it doesn't work. You memorize something, it's all tangled in your head, you can't even tell if you remembered it right or not. But my first year chemistry instructor had me memorize 6 polyatomic ions and 6 strong acids. We've already done the polyatomic ions. Here are the 6 strong acids. Now, I hope you can say the names before I do. I'm going to name them slowly. Hydrochloric acid, hydrobromic acid, hydriodic acid, nitric acid, perchloric acid, and sulfuric acid. And sulfuric acid is a special case. Even though it has 2 protons, only one of them comes off completely. So only the first ionization is strong. That's a list of 6 things to memorize. You can kind of chunk them together though. That makes remembering easier. These 3 are halogen acids, HCl, HBr, and HI. The only halogen acid that is not a strong acid is HF. It's weak. Now, I'll apologize to you now. In this first course, we got to take a lot of information as authoritative knowledge. I hate that. By the end of the year, you will be able to justify why HF is weaker than the others, and that will make it easier to remember. It will feel more like remembering than memorizing. But for now, I'm afraid it's in your interest to memorize these. All right, strong acids are a type of strong electrolyte. Let's move on to weak electrolytes. They are electrolytes. They make charges in water, but they are less than 100% dissociated. They are less than 100% converted into ions. And you're going to watch out here for weak acids and weak bases. Whoops, and weak bases. How are we going to recognize those? Well, let me tell you, it's not as easy as you might think. All acids have H+, but not everything with an H in it is an acid. And all acids that aren't strong are weak. How are you going to recognize them? Don't worry. I'm going to make it so that it's pretty clear. Let me tell you what my favorite weak acid is. My favorite weak acid I've introduced to you before. It's acetic acid. which is what you dissolve in water to make vinegar. You might see the formula written in different ways in different textbooks. Sometimes you'll see it written as HC2H3O2. And I think the book writes the formula like that to show the hydrogen at the front to say, woohoo, it's an acid. I'm not going to write it like that ever again. What I'm going to do is write it as you see it here, CH3COOH. That gives me a little bit of hint into the structure. Again, I have to apologize for authoritative knowledge right now, but by the end of the semester, you will be able to draw the structural formula for acetic acid. And when I do that, you'll see that the way it's written chunks it out. I've got a carbon with 3 hydrogens attached to a carbon with a double bonded to an oxygen attached to an OH. So that's how you're going to see the formula. Just as a little foreshadowing for people who are interested, many weak acids have this particular chunk in it, this group of characteristic atoms, this particular functional group, if you've heard of such things. But we'll talk more about that later. All right, so what are we going to do besides plug in my electrical cord? We're going to write an equation for what happens when acetic acid dissolves in water. So to be able to write this equation, first I have to recognize that that formula is acetic acid. I'm telling you now, and I'll tell you later, and you'll tell me later, that that is your favorite weak acid. I want you able to recognize that as well. Once I know that it's an acid, I know what acids do. They react with water. And how do they react? Acids donate hydrogens. Acetic acid is a monoprotic acid. It only donates 1 hydrogen. That's why in this kind of formula, they put only 1 hydrogen at the front. And it would be that one, for reasons we'll see later. So what do acids do? They lose H+. Now that it's charged, it's attracted to the polar water, it becomes aqueous. The acetic acid lost the proton, the H+, the water picks it up to become hydronium. And again, there is the species that indicates I have an acidic solution. But I'm not done. I have to change one thing. Strong acids completely react, but weak ones only produce a little bit of the product in equilibrium with the starting material. And for a weak acid like acetic acid, when we reach that state of equilibrium, we reach that state of balance, most of it stayed intact as neutral molecules. This picture doesn't show many of the particles. Really, there would be maybe more than 95% intact molecules, and only less than 5% would react to produce positively charged hydronium ions and negatively charged acetate ions. So it is an electrolyte. It produces charged particles in liquid so they can move. But because we make so few ions compared to neutral molecules, I don't have as many charged particles, and the light bulb doesn't glow as brightly. So that's my story of acetic acid. That's my favorite weak acid, and now it's yours. Nudge, nudge, wink, wink. What I see for ammonia down below, that is my favorite weak base, and it better become your favorite weak base. But once we know it's a base, we know what it does. Ammonia, which is a gas when it's pure, not only dissolves in water, but reacts. We saw that acids donate H+, bases accept H+. So we're going to go from neutral ammonia to charged ammonium. And because it's charged, it's attracted to the polar water molecules they surround it and make it aqueous. The water lost H+, now it's just hydroxide. And there's the hydroxide that indicates to me I have a basic species. One more thing. This is a weak base. It's a weak electrolyte. So I'm going to add reversing equilibrium arrows there. And when this particular one comes to equilibrium, again, you've got way more neutral ammonia molecules than ammonium and hydroxide ions. So that's why it's a weak electrolyte. Last category, non-electrolytes. They dissolve in the solution, but if I put some ethanol in my beaker and dissolved it, you would see that they don't break into ions, they stay as neutral molecules. Because they're not charged, they don't conduct a current. Now, in this picture, it's ethanol, which is that molecule there. I don't need you to know that. Again, to the same animation that I pointed out to you before, you can add, instead of salt, you can add sugar to the beaker, and you will see this same thing, that there's no conductivity for these non-electrolytes. The light bulb doesn't come on. Now, how do I know that they're not electrolytes? Think back to the previous video when we saw what happened when we dissolve things in water. Whatever particles were already present swim free in solution. If I have an ionic compound, ions swim free. If I have a polar covalent compound made up of molecules, molecules swim free. So this is a formula for ethanol, the booze molecule. I see only nonmetals, so it's covalent, it's made up of molecules. And what happens when it dissolves in water, which it does, that's how you make vodka, it becomes aqueous. Don't you dare break covalent bonds when you dissolve something. The state has changed. It's a physical change. It used to be that the ethanol molecules were packed in amongst each other in the pure liquid, but now the ethanol molecules are separated by water molecules. They're aqueous. Now, let me distinguish between dissolving and dissociating. Ethanol dissolves in water. It ends up surrounded in water. And if you looked at a solution of ethanol in water, it would be homogeneous. You don't see two different layers. It dissolves, but it doesn't dissociate. I want to contrast that with something like the oil in our salad dressing before. I wouldn't even think to try to classify that as some kind of electrolyte because oil doesn't dissolve in water in the first place. Doesn't make much sense to talk about it dissociating, breaking into ions, if it didn't even dissolve in the water in the first place. On to my last example here. I don't need you to know this, but I would tell you if you needed to know this, that C12H22O11 is the formula for sucrose or table sugar. And you don't even have to know that to be able to write an equation for what happens when that dissolves in water. The first question I always ask myself is it ionic or is it covalent? There's only nonmetals, it's covalent, it's made up of molecules. So what's going to swim free are sugar molecules. When you dissolve sugar in your hot coffee, the molecules are still sugar molecules, they're just separated by water molecules. So sugar dissolved, it's not a solid anymore. You can see a homogeneous solution when you dissolve it in water, but it didn't dissociate. It didn't make ions. And because there are no charged particles in solution, the light bulb doesn't light up. Let me summarize everything we've done in this section with a little decision-making scheme here. If I want to know what happens when something dissolves in water, which will be essential for writing more complex chemical equations later, I'm going to consider things that are soluble in water. Only things that are soluble in water. Ionic compounds and polar compounds. The nonpolar ones won't dissolve in water in the first place. They won't even dissolve, let alone dissociate. The question I'm going to ask for things that are soluble in water is it ionic or is it covalent? That is the main question, because whatever particles were originally present, you end up with in solution. If I have an ionic compound, I get ions. If I get a covalent compound, I get molecules. There are only a few exceptions, and those are the strong acids, and weak bases. The strong acids are also strong electrolytes. They completely react. Forward arrow to make ions in solution. The weak acids and weak bases, though, only dissociate a little bit. So it's mostly molecules in solution for them too. Yeah, there's a few ions. The light bulb will come on dimly. It's a weak electrolyte. We'll show a little in equilibrium, but mostly it's molecules left in solution. And don't worry, we'll apply this and cement it by practicing it a lot in the next section.